Hi, folks. Thanks for joining in. Let me just check if everything is working as expected before we dive in. That's why I came in a couple of minutes early. So just give me a second. Okay, let's see how the whole video stream is working now. So yeah, I don't see any issues whatsoever. Yeah, I can hear myself here fairly well, and no issues whatsoever that I can see here. Yeah, I also opened the live chat session, live chat right side window. Hey, folks, thanks for joining in. Yeah, I don't see any hiccups from my side. The stream is pretty stable. The internet speed is also pretty good. So hopefully we'll have a good session this time. Okay, sounds good. Sounds good. Okay, it's good that nobody has issues, which is good. So let's wait for a few minutes for everyone to join in. Since I'm a little early, and some of you are also a little early, just like me. Before we get started, I mean, if there is anything that I could, industrial IoT and machine learning is gold. Yes, there is a lot of opportunity there. There are a lot of very interesting startups also in that space. So I'll also touch upon some startup opportunities in the later parts of this session. Uh, okay, sounds good. So things are looking good. Uh, okay, good. So no major issues whatsoever today. Things are good. Things are looking good. Uh, yeah, nowadays we're doing like 2 3 live sessions across multiple courses that we have. So we are more or less streamlined the live process itself. Okay, this looks good. Yeah, I think we're a little early, but let's keep going. So somebody's asking. Okay, let me answer a few questions from the chat window while others join in. I'll probably start the session at between 10:03 and 10:05, 10:03 and 10:05. Let's give some time for everyone to jump in. So somebody's asking, can we deploy sklearn models? Why not? I mean, sklearn is a pretty good library nowadays. I've seen real world productionization of sklearn models. Again, it depends a lot on the requirement. If you're working at an internet company where you have to return the class label or the regressed value in, let's say, in 1 millisecond or 2 milliseconds, probably sklearn won't work. But if you don't have those low latency constraints, why not use sklearn? Again, sklearns, some of the algorithms in sklearn are bad. For example, the random forest and gbdt implementations in sklearn are not really that good. xgboost is a better tool there. So I've seen, like, we have used XGBoost in my own teams. I've also used sklearn, depending on the context, right? Where again, what tool to use depends a lot on what are the engineering constraints that you have. Do you have a scale constraint? Do you have a latency constraint? So if you don't have those constraints, you can happily use sklearn if you have the right model that you want, which is well implemented in sklearn. That's not a problem at all. Uh, So, okay, I'm not from a coding background, neither from stats. Can I be part of this industry? Anish, that's a very good question. We have seen people from non-computing and non-math backgrounds also transition to the industry, to the machine learning industry itself. Like we have some students from pharma background, right? We have learned some programming in their BTech first year or so, but they've forgotten most of it. So my suggestion for you to evaluate if you're really ready for transitioning to machine learning is to check out our free videos. We have like 15 to 20 hours of free videos. You can just log in. It's free to check out. So where we cover some basics of Python, some basics of exploratory data analysis, some basic concepts in probability, some basic concepts in linear algebra, and a couple of machine learning models. So if you could spend some time going through these free concepts, freely available concepts on our website, and see if you're able to follow through that. Again, please try to spend ample amount of time. Since you don't have background, you might take more time than others to follow this. So try to follow these contents. If you're able to follow it, you can certainly transition to a machine learning role. If you cannot, probably this course and in general AI machine learning may not be that apt for you, to be honest. Um, uh, So MS from US, if you get a good university, actually we did a live session. You can actually check it out on Applied Course. So because at Applied Course, we have a GATE course, we have an interview prep course also for computer science students. So we did a live session recently on this career choices, because there most of our students are undergraduate students or working professionals with under 2 years experience, right? For at AI course, we have a much broader spectrum. We have people with 15 years experience to somebody who is a BTech first year student, right? So that's why we have done a live session that is available right now. Just go to Applied Course YouTube channel. We had a very good discussion, lots of options on how to think about it. Again, we also compare MS in US universities, masters in Indian universities, getting product-based company jobs, getting machine learning jobs. That whole spectrum we have compared in that live session. So instead of taking time from this, I recommend you check out that. Again, for our registered students, anyway, we have like every 3 weeks we do 2 live sessions, roughly speaking, because we plan to do at least 35 to 40 live sessions, typically 35 plus live sessions in a year. So we have started covering these advanced topics. Like last week, I think last week we did cover generative adversarial networks, how to write code for GANs and TensorFlow and Keras, etc. So we will also do a session on advanced topics or on new things like TensorFlow 2.0 or TensorFlow in JavaScript. We'll do those in the live sessions, okay? Because in 2 hours live session, if I have just one model to explain, I can easily do that, right? So we will keep adding content to our course based on advancements. Again, the course itself is very dynamic, which means we add new stuff as time progresses. And this comes both from recommendations from students as well as from industry, what is changing in the industry, right? So, okay, that's good. So even in US, actually, we have significantly fewer students in the US than in India. But thankfully, we have a decent network of recruiters even in the US. So the job guarantee program works exactly the same as in India. Nothing changes. It's just that we have fewer students and hence our network of recruiters is smaller than in India. In India, our network has grown massively over the last 6 to 9 months. While in the US, it's still smaller because we have fewer students, to be honest. And we've been focusing mostly on India because most of our students have been here for the last year and a half to 19, 20 months now. So, but the job guarantee program works exactly as is in the US. Somebody's asking about Singapore. We don't have it right now. Again, we need a critical mass of students to be able to build that recruiter network. Right now, some students in Europe have also asked us. We have some students from Europe who have successfully gotten placed, but the number of students is so few that building the recruiter network, the recruiter will simply ask, okay, can you give me 10 students a month? I'm like, sorry, we don't have that type of volume in Europe or in Singapore or in Southeast Asia. So that's a chicken and egg problem we are going through. That's why we are not rolling out our job guarantee program outside US and India, where we are fairly confident about it. Okay, sounds good, guys. I think we should get started. Okay, thanks. It's anyway 10:05, so let's get started here. Thanks for joining in, everyone. So let me give you the agenda for this live session itself. In this live session, we want to start off with explaining what are the beautiful applications of IoT. I've also talked briefly about some of them in the announcement video for this live session. Now we'll go into some more depth. I'll also talk in lots of detail, again, on the architectural components. What are all the pieces that you need to work, that you need to build for building an IoT plus machine learning applications, and actually how to actually take it to production. So we'll look at the whole end-to-end pipeline, and I'll use something that we worked on, as in we mentored a startup. This is a startup where we have experienced mechanical engineers, industrial engineers, and software engineers and machine learning folks. We mentored this startup at the very beginning. The startup has progressed. It has found a nice product market fit right now. They're already testing the product at multiple large factories and industries across India now. So we'll also get some insights. We'll also share some insights on how we mentored the startup and how we built it end to end. Having said that, I'll also focus on other applications of IoT in healthcare, in predictive maintenance and industrial internet, partly on smart farming. I'll give you again, this discussion is not a dive deep discussion because in 2 hours, I can't teach you everything in IoT, to be honest. Okay. But what I'll give you is I'll give you a 10,000 feet view of what are all the pieces that you need to build an actual product in the marketplace for IoT and machine learning. I hope people who are either working software engineers, startup enthusiasts, everybody would benefit from it, because you could be working at a company and say, okay, our company already has so-and-so tools. Why don't we launch new products? Okay. So I'll give you that big 10,000 feet view of how IoT, all the hardware components, all the microprocessors, microcontrollers, how all of the data pipelines, how machine learning, everything fits together from the viewpoint of a few examples. So by the end of it, you will be able to think about how to design a high-level system. Again, we are not going into the nitty-gritty details. For example, I will not be able to teach you, because of time constraints, on how to program a microcontroller like a ESP8266 or ESP32 or a Arduino. I'll provide you links to that, but I'll not be able to dive into those nitty-gritty details. Okay, I wanted to give you a big picture view of it, so that when you think of any application, or if you're thinking of a product or a solution or a startup, you know what all pieces need to be there and what all areas you need to have reasonable expertise in. Okay, so with that, let's get started now. Okay, let me just share again. I'll share the notes at the end of this session. Okay, let me share the screen quickly. So the whole notes that I had was this. This is my notes. Okay, I'll share this Google Doc with you at the end of the session. I'll post it below the live session video itself. Okay, so this is the big flow. So if you notice, we'll start the flow with some basic examples, right? We'll start with okay. Let me show you here. IoT plus machine learning. Why is this combination so deadly? And what are all the applications? We'll walk you through a startup that we mentored. So I'll walk you through the whole problem end to end here, right? So what are all the stages and what did we do in each stage? What are the choices that we had in each stage? So you can think of this as a high level architecture overview, right? Then we'll discuss about how to build end-to-end systems in healthcare with some case studies on some real world problems, that real startups which are actually solving super interesting problems. We'll also take up something in smart farming, and then we'll summarize everything, all the building blocks, the choices we have with the high level architecture, and I'll walk you through a few examples at the end again, right? So I hope this gives you some idea on where we are headed. Okay, so let's go step by step now. Again, I'll take breaks in between. Unfortunately, we'll not be able to go too deep into too many topics, unfortunately. Okay, so let me stop this. Let me change it to the camera view. Okay, so this is where we are. Okay, sounds good. Okay, just a second. Yeah, so this looks good. So let's get started. Okay, wherever I have some resource that I want to show you, I'll change it to the screen sharing mode and I'll explain you those components. Okay, the very first thing that I wanted to go over is applications of IoT. Okay, so what does IoT basically mean? So let's go to first principles. Let's try to understand this from the first principles perspective. Suppose you want to build a machine learning model. Okay, you want to build a machine learning model. What do you need to build a machine learning model? Of course, you need some expertise in machine learning. You need tools like scikit-learn, TensorFlow, XGBoost, all the software tools. You need computational resources, all of that. But even if you have all of them, if you don't have data, you can't build a machine learning model. Without data, there is no machine learning model. So the most important component of a machine learning model is actually data. Okay, because if you have large amounts of data or good clean data, then you can pump that data in. Rest everything is readily available. It's very easy to get computational clusters and computational resources on cloud computing resources like AWS. You can even train it on your laptop or your gaming desktop. Right? It's fairly easy to do that today. Okay, you have beautiful and brilliant software tools like TensorFlow, Keras, scikit-learn, XGBoost, brilliant tools. Okay, that's not a problem. Computational resources are cheap, and you have software tools. And learning machine learning is also not rocket science anymore. It's fairly doable. If you put in 5 to 6 months of good effort, you can learn the basics of machine learning and start building real-world products and solutions using machine learning. Right? So once you have the machine learning component, the biggest piece that is missing is data. Okay, so how do you acquire data now? For example, let's take some examples, right? Okay, so if you look at social media, where does the data come from? In social media, data comes from people contributing the data. If I add you as a friend, that is very important critical information that I'm providing a social network like Facebook or Instagram, right? Or Twitter. If I'm following somebody, that's a very strong data signal that I'm interested in this. Or if I click on a post by somebody and if I read that, that's very strong signal that's the data that I'm generating. So who is generating the data in social networks? It's consumers or users of social networks. In the case of, let's say, Amazon, okay, what are the sources of data? People's search habits, people purchasing habits, sellers putting their products on Amazon, sales data. See, all these are also because of human activity. At the end of the day, a lot of data for social networks or for e-commerce systems comes from human activity. This is human generated data. Even in search engines like Google, right? One source of data is the whole internet itself, right? Every page on the internet, they almost try to crawl as many pages as possible on the internet. So the crawl data, the second source of very strong information for Google search is the hyperlinks, right? It's a link from one web page to other web page. And who is actually created all these links? Humans again. It is humans who created these links. It is humans who created these web pages at the end of the day. And when you search for something, if you click on a search result and if you go and spend sufficient time there, that is again data to Google showing that, okay, this search result was relevant for this query for this person, right? So that's also human generated data. So a lot of applications of what we see typically as machine learning systems at internet companies, most of the data is human generated data. So in a nutshell, if you think about it, let me just share the screen here. Let me just share the screen quickly. So in a nutshell, most of IoT plus ML has two components. There is data and there is modeling. Modeling basically means machine learning models here, right? And we keep hearing these things like predictive maintenance or Internet 4.0 or smart healthcare, smart farming, smart homes, smart cities. We keep hearing these terms in the media, right? But what do they actually mean? At the end of the day, anything which has the keyword smart nowadays basically implies there is a machine learning or an AI system, machine learning, deep learning, or some form of AI system, and there is data involved here. That is the most important part, right? So I hope again, in the case of IoT, the most important differentiator here is if you look at e-commerce, okay, if you look at not just e-commerce, if you look at companies like Amazon, right, Facebook, Google, right, Twitter, all these companies, most of the data is human generated. Most of the data is human generated. In the case of IoT, see, and these companies have leveraged this data phenomenally well, right? But in the case of IoT plus machine learning, this data is generated from sensors. This data is generated. I'll show you some examples of what sensors are, right? So most of this data is generated using sensors. Right? So that's a fundamental difference between IoT plus machine learning and traditional machine learning applications that you have encountered across the internet. For example, okay, let me tell you one very interesting thing that is not obvious. If you look at Uber, Ola, or any of the other very interesting cab services, I would call them more of an IoT application rather than a smartphone application. Because what does an Uber use at the end of the day? Uber uses your location. That location is obtained using the GPS chip that you have on your smartphone, right? So you can think of Uber, again, many people don't connect these dots. Where does most of the data for Uber come from? Uber's data comes from the location of the riders and location of the cabs. And where does that location signal come from? It comes from GPS. Of course, Uber has tons of models, some of them machine learning models, some of them simple statistical models. It has models to decide which user should be allocated to which cab. So user I should be allocated to cab J, right? What is the fastest path from user I to cab J, right? How much should I price for this ride? So all these are economic models, statistical models, and machine learning models. But a huge chunk of data itself, again, I'm not saying this is the only source of data. People pay Uber using their credit cards, using their Paytm, etc. That's also data. But a very critical component of data that Uber obtains is from the GPS signals. Okay. So, and GPS, you get it because of the GPS chip that you have, right? So if you think about it broadly, IoT plus machine learning is very much like your internet applications, except that This data is generated using sensors. That is a broad view of thinking about IoT plus machine learning. This is the broadest view. Again, let's walk through a few examples so that you have a bigger picture view of things. So let me explain you. Let's pick this problem, right? Let's pick this problem of predictive maintenance. I'll go into lots of details here, and I'll use this as an example to explain all the components that are there in a building an IoT plus machine learning application. The challenges, okay, I'll walk you through because we have first-hand experience of mentoring a team that built it, which is in a prototype stage and things like that. First, let's define the problem. Okay, so for some of you, this problem might look like beautiful. For some of you, it will feel boring. So, but I hope this gives you a big high-level overview of what are all the components that you need to build, right? Then I'll walk you through some examples in healthcare, some examples in farming also. Okay, so let's use this as a starting point. Then we'll move to other components. First and foremost, see, again, when this startup started, we asked a very simple question. What is the problem that we are solving? Who is the customer? What is the problem that we are solving? So then again, thankfully, we had industry veterans who are working on this problem, who have like 10 to 15 years of experience in predictive maintenance of sorts, right? In maintaining large industries. These are people with terrific experience in that field, right? So let's understand what is predictive maintenance first. What is the problem definition behind predictive maintenance? Let's see this. So in a factory, if you think about a factory, right? So let me just walk you through this, okay? Take a factory, right? A factory has lots of machines. It has tons of machines. And many of these machines are like your motors, right? Motors, rotors, generators, turbines, right? Many of them. Actually, a reasonably large-sized factory. Let's say, let's take a steel plant. It will have tens of thousands of motors running to power hundreds of devices, right? And these motors come in all shapes and sizes, right? So with so many mechanical or electromechanical equipment, one of the biggest concerns for them, and these are very expensive. These are very expensive stuff. Okay, many of these devices are super expensive. And if anything goes down, the other big problem here is if anything goes down, the downtime can cost millions of dollars. For example, imagine you're running a steel factory, a steel plant, right? Steel plant continuously generates sheets of steel. Okay, there is a lot of chemical processes, and then there are lots of equipment through the whole processing pipeline. It generates steel. Now imagine one of your motors, critical motors, goes down. What happens now? Your whole steel plant comes to a standstill, which means all the other motors have to be shut down. The whole processing pipeline has to be shut down. That's what is called as downtime or unpredicted downtime, right? Or downtime which we don't want, okay? Because that downtime will cost millions of dollars, to be honest with you, for reasonably sized factories. Again, we'll use a steel plant as an example. This could be any factory. This could be a paper mill. This could be an oil rig. This could be a solar power plant. Sorry, not a solar power plant. This could be a what do you call it? A wind turbine system. Anything which has all these moving parts. Okay, that's the core of it. If something fails, that's it. So what they do is they do something called as regular maintenance. So they perform something called as regular maintenance. Okay, wherein they literally every week or at some regular intervals they check the machine which is in running at that point, and if there is any problem, they'll probably inject some oil into it. So some mechanical engineering stuff where I'm not an expert in. Okay, so there is a regular maintenance. Now, what predictive maintenance? Again, remember that these tools, okay, or these equipment is super duper expensive. These almost cost like 80% of the cost of setting up a factory. So, which means if you can somehow increase the lifetime of these equipment, okay. So you want to be able to predict failure. See that the couple of objectives here. You want to be able to predict any failure or any malfunction early enough, number one, and you want to be able to take diagnostic steps, right, to ensure that the lifetime of these critical expensive equipment is also increased. Okay, so these things can be very, very expensive, trust me. I mean, companies could spend millions, even tens of millions of dollars. So companies like General Electric, the Tatas, right, in India, who are large manufacturers, they could be spending hundreds of millions of dollars to ensure that their devices and their technology and their equipment runs smoothly. Right? So, and people have been doing it. This is nothing. People have been doing this for the last 30 plus years. Okay, this is not a new field. Okay, there is a lot of interesting research in this space. Now, what is happening right now is this. Okay, so imagine this. Okay, this is my time axis here. This is my time axis. I have a bunch of sensors here. Okay, I have a bunch of sensors. Visual inspection. Okay, because factories have engineers working, they can visually inspect. They can look at some readings like temperature, etc., oil readings, right, or some accelerometer data. Okay, so they can look at all of this data, and whenever, again, typically, so traditionally, what's been happening here is people can predict these failures. People can predict these failures. Okay, it is possible using some sensors. Okay, I'll talk to you about some sensors in a little while. So these sensors are typically like accelerometers. Okay, or accelerometers are the most widely used sensors to detect failures of machines. Because what does accelerometer measure? Accelerometers measure, again, these are not the accelerometers that you have in your smartphones. These accelerometers are industrial accelerometers. Okay, these are called as industrial accelerometers, right? And these accelerometers are extremely sensitive, extremely powerful, and they can detect even the smallest of vibrations. And typically, if you have a mechanical issue like a bearing failure or anything like that, okay, the vibrations increase dramatically. Imagine earlier the amount of vibration is very small. Suddenly there is a spike in vibration. There is a sudden change, right? And when the change happens, the mechanical engineer or the maintenance engineer goes and says, okay, there is a problem here. Let's actually grease it better, or let's do some fixing. Of course, he's a mechanical engineer, also a specialist in maintenance, so he would know how to do it. But the biggest problem is this: right now, in the current world, people are waiting for weeks, even months, before an explicit vibration increase is shown. They're spending a lot. See, by the time they detect a failure right now, the machine has already taken a hit. So while there is some method right now which uses sensors, accelerometers, etc., this is the technologies that they have, the methods that they have are still old school. Okay, so they do use sensors today, and they've been using it for the last 3 decades or more. Okay, but the methods they have are not computational. The methods they have are not AI driven, which means by the time they detect a failure, it's already quite late, right? So the goal of this whole project was, can we detect failures early on? The problem definition is diagnose machine failures early on. Diagnose machines. Okay, diagnose machines earlier. Again, we'll also see in healthcare applications where we want to diagnose humans faster. Okay, so here it's about diagnosing machine problems earlier so that I can take preventive maintenance. Okay, I'm predicting when an error might happen. So here we try to predict in how many days or in how many weeks will a problem arise. Based on that, I know the severity of the problem and I'll take preventive measures to start with, thereby increasing the lifetime of equipment. And remember, equipment could cost 80% of your total money that you invest in a steel plant or in a power plant or in a let's say in a paper mill, right? In all of these factories, huge chunk of investment is equipment and land, right? So what we said was this: okay, there is already a bunch of sensors that people are using. What can we do about it? Okay, so problem definition is clear. Again, since we had industry veterans as part of the startup team, they knew the problem firsthand and they were very clear. Of course, they also talked to potential buyers beforehand, pitched them, and they said, yes, if we have a solution for this, we are willing to try it out. So right now we have a working prototype that is actually installed in some factories across India, and we are mentoring the team mostly on the IoT. So the team has a lot of expertise in mechanical systems where we don't have any expertise, right? So we don't have to worry about it. So most of our help has been in IoT and machine learning components. Okay, this is where we came in. Thankfully, the team also has a few machine learning engineers that they've hired, and they're building the whole setup. Now let's look at what all sensors do we need. Okay, there are multiple sensors here. So the problem definition is clear. The first thing that you have to think of is, what sensors do I want to solve this problem? Traditionally, we have seen accelerometers being used. Okay, accelerometers have been used for the last 3 decades to diagnose machines. So we said, okay, can we use these accelerometers? Why not? But the problem was, most of the accelerometers that were sold by large companies, and they would actually, so these accelerometers are like this. Okay, let me so the typical sellers of these accelerometers now is, they sell the accelerometer plus a device which measures everything, and you can't get this data out of the device. They won't let you export this data to your own software. They don't do that because they're frightened that somebody will replace them. Okay, so there are devices which will give you some, so it will measure acceleration, it will give you some initial analysis, but it won't let you export the data to your own software. So we said, okay, so that's one problem. Then there are also ultrasound sensors. Okay, I hope all of you understand what ultrasound is, right? We humans typically listen to sounds in 20 hertz to 20 kilohertz, right? Again, only younger kids can hear closer to the 20 kilohertz. I checked, I can't hear more than 15 kilohertz myself, 15, 16 kilohertz, right? So anything which has a higher frequency than this are called ultrasound. Typically, bats can hear ultrasound, dogs can hear ultrasound, rats can hear ultrasound, right? Some insects also can hear ultrasound. They can also generate ultrasound signals. So there are also some interesting companies which use ultrasound plus a device, but they don't let us export that data. So we said, okay, we are not able to get the data to see, at the end of the day, here is a sensor. The sensor has to give data to my machine learning system, right? If I'm not able to export this data, I cannot build a machine learning system on top of it. Okay, so we said, okay, no point using the existing solutions. So we started acquiring accelerometers from manufacturers in China and in Europe. Okay, so the team actually obtained accelerometers and ultrasound sensors, right? From both, they imported some of them from China and some of them from Europe, right? Especially from Germany, where there's a good industrial research there. Okay, then we said, okay, why should we just use these two? Why can't we use other sensors? For example, another sensor that is there is cameras. Very cheap. Camera is also a sensor, if you think about it. So we said, why can't we use cameras also? Because they're there in every smartphone, right? So we said, okay. So the team actually imported accelerometers, ultrasounds, cameras anyway had smartphones. So we didn't have to import some special software. Then we said, okay, so I have my sensor first, good. My problem definition is clear. I know what data to collect. Now to collect this data, look at this. A typical sensor, let's assume this is your ultrasound sensor, okay? Ultrasound sensor will have a microphone like this, okay? So this is a microphone, it can listen to ultrasound, okay? It will convert this into electrical activity, okay? It will actually convert this to electrical activity. It will take sound energy. That's what a microphone does, right? A typical microphone that you have in your laptops, in your smartphones, it actually takes sound energy, converts them into electrical activity. Now I need to convert this to digital signal, right? So typically what you do there is, again, thankfully, we took some help from electrical engineers, and some of these circuits are readily available, right? So this would actually generate some electrical energy. We would have an A to D converter. Some of you may have studied this in your BTech, especially if you're a computer science student or an electrical engineering student or an electronics engineer student. You might have learned about A to D converters, analog to digital converters. So it will take an analog voltage or an analog current, and it would convert that into a digital signal, into zeros and ones, right? So this is the first step. Building this A to D circuit, again, this requires understanding of electronics, right? This requires understanding of electronics, digital logic circuits, all of those parts. So to actually build IoT plus machine learning systems, I think you need to have a wide spectrum of skills, from basic electronics, breadboards, circuit boards, to cloud computing and machine learning and deep learning. So there is a huge spectrum of skills that you need. Actually, while solving this problem, initially they did not have an electronics engineer. So we helped them, and I ended up reading up some of the textbooks from my BTech days. So then I connected the dots and said, okay, this is why we were taught all these basic electronics, even for a computer science student. We learned about oscillators, we learned about all the basic stuff, right? I think we had electronic circuit design or something. We had 2 semesters during my BTech days. So all the basic electronics that I learned was helpful, but soon we had actually proper electronics engineers who could do it much faster than we could. Okay, so now once I got the data as digits, right, I need to be able to store this data and transmit this data. The next component here is store the data and transmit this data to a server. Okay, what do we do there? See, to store the data, maybe I want to do some simple basic processing also. Okay, the 3 pieces here, if you think about it. The first piece is whatever data is coming in through this, I want to store the data first. Then I might want to do some simple processing and then transmit this data to a server. Now, this is where something called as edge computing comes into play. Edge computing basically means computing at the very edge of systems. So this actually, if you think about it, this is actually right next to the motor. This is where you have your motor. Right? This is where you have your actual motor. So you have your sensor here, which in this case is an ultrasound microphone or an accelerometer or a camera. You take all of this data. Here you have typically a microcontroller. Again, if some of you recall, electronics engineers, electrical engineers, computer science engineers, we studied about processors like 8086, 8085, and microcontrollers like 8051 during our BTech days. Right? So what is here is actually a microcontroller, literally a small sized computer, okay, which has small amount of RAM. It also has some small amount of storage space, right? It also has small amount of compute. Okay, it can do some compute, and typically the modern microcontrollers that we can get. So the microcontrollers we ended up, again, the more popular ones, what we studied in college are no more used as widely. The more popular microcontrollers right now are Arduino based microcontrollers, right? Then you have Raspberry Pi based microcontrollers. And the very popular one is called ESP8266, and the next generation of it called ESP32. Very, very popular devices in the IoT community. So we started off with the ESP8266, then we moved to ESP32. What these devices, these are like small chips. I'll show you a simple example of how small this chip is. Okay, this is what predictive maintenance is. This is how an Arduino board looks like. Okay, this literally has a small chip, okay, where all the compute takes place, and there are a bunch of IO, input output. If you ever been to a microcontroller or a microprocessor lab in your BTech days, you would immediately recognize this. So this is a much better chip. Okay, so this chip is referred to as the ESP8266 chip. I think it will be written somewhere here also. Somewhere here it's written ESP8266. The good thing about this chip, unlike other chips, is it has a processor, small processor. Obviously, it has a RAM. It also has some permanent storage, like a SD card. I can attach an SD card to this, right? I can also permanently store data, and the power consumption is very, very small here. And most importantly, it has Wi-Fi built in. It has Wi-Fi built in. Look at this. It says Wi-Fi here clearly, right? So it has a Wi-Fi chip, the processor, RAM, everything on literally one single chip. This single chip has a processor, it has a RAM, it has some permanent storage, it has Wi-Fi, everything in a small chip. Okay, that's the power of these chips. Okay, again, a lot of nice innovations have happened over the last 5 to 10 years in this space. Okay, so we started off with ESP8266, but ESP32 is a better version, and I think the team currently uses ESP32. So what it does here is it takes the data, stores the data, does some simple processing, and it uses Wi-Fi. Transmission happens through Wi-Fi. Again, there are modern systems. So to transfer all the data, see, first this microcontroller like Arduino, Raspberry Pi, they're actually collecting the data, storing the data, and then they have to transmit it. The transmission happens through Wi-Fi, sometimes over 4G networks or 3G networks, depending if this motor is in a very remote location, okay, where I can't have a Wi-Fi router or anything. I could also have cellular connection like 4G or 3G there. Thankfully, with Jio and Airtel doing a terrific job, we can even have 4G networks very, very far away. There is also the third very interesting thing called as Bluetooth Low Energy. Okay, BLE basically stands for Bluetooth Low Energy. This is super duper powerful here because I can actually transfer data via Bluetooth. Okay, I can transfer data via Bluetooth from this system to probably a central hub. I could have a central computer here. Okay, I could have a central computer or even a smartphone in this case. You could have, because a smartphone is a fairly, if you take a slightly high-end smartphone, like I think what the team currently uses is a OnePlus 6, if I'm not wrong. Okay, which has a pretty good Qualcomm processor and all of that. It has a fairly good Bluetooth, right? So the transfer between this and this could happen over Wi-Fi. It could also happen over 4G, but Bluetooth Low Energy is the best, right? Because as the name suggests, one of the biggest challenges in designing these systems is the power supply. Suppose if I leave this in near a motor or near a set of motors, how long will this whole system last? If I have to keep replacing the battery, I'm going to die. So for battery, typically they use regular lithium-ion batteries, or they use solar power. Okay, so I think the team ended up going with the simple battery system. And there are some software components that you can write to ensure that your battery is not unnecessarily drained. Okay, so Bluetooth Low Energy is super good because it consumes much less battery. And again, for edge computing, the reason why we use very low power microcontrollers is because of battery. For most IoT applications, how you power your sensors, how you power your microcontrollers or edge computing devices is an extremely important question to answer. So once all this data came in, look at this, once all this data came in, so everything talks to a computer or a smartphone. In our case, it was a smartphone. This goes to the server. Okay, all this data goes to the server, and we had our servers on AWS, Amazon Web Services, cloud computing servers. Now, look at this, look at how the whole flow worked now. Again, the most challenging part in this was designing the hardware components, because the team itself did not have hardware expertise. But if you have a good electronics engineer and a good computer science engineer who can write this code very well, right? Who can also, again, very, very importantly, you have to be extremely careful about battery. How you design the battery and power supply systems is super important for this, right? So finally, your data is in a server on AWS. Now what do I do? So all of my sensor data, my accelerometer data, my ultrasound data, we also had temperature sensors. I forgot to mention that. Okay, we also, again, these sensors are fairly cheap to buy. Okay, we had some temperature sensors, then we had some cameras. Again, I'll tell you something very interesting that we are doing with cameras here, because we know so much of computer vision anyway. So, okay, all this is cool. So we got all of the data now into my server. Now what do I do? So what I do first, as a first step, instead of jumping to machine learning and deep learning systems, the first thing I do is what have the other companies and what is the literature existing in this space? For example, let me give an example. In this space, let's take a simple example of accelerometers and ultrasound. Okay, over the last 30 years or so, lot of mechanical engineers and scientists, especially at large companies like General Electric, they've done tons of research, and they've shown that if I just compute the fast Fourier transform, okay, we discussed about what fast Fourier transform in lots of detail in the codes anyway, right? So they compute simple fast Fourier transforms, okay, the simple FFT of because this is a time series signal. This is also a time series signal. This is like audio signal. This is also like a accelerometer vibration signal. So most of the systems that are currently existing they first compute the FFT, and they have a bunch of rules. Rules could be like, okay, at 30 kilohertz, if you have a spike in your FFT, then this problem might occur. Okay, if you have a peak, if you have a spike at 30 kilohertz and also at 60 kilohertz, then so and so problem occurs. Those are typically referred to in machine learning as rule-based systems. So the first thing we did was, let's implement the rule-based system. So we implemented the rule-based system. Now, if you look at it from a product perspective, if you look at it from a pure product perspective, all these steps are being currently done by our competitors, except for the cloud part of it. So their devices, so what do they do today? They actually have a sensor. They actually have a sensor and they have a device, and they can see all of these FFT, everything they can see on these sensors. And these things can cost like crazy. I mean, the prices can be anywhere from 15 to 20 lakhs in Indian currency, rupees, right? And these sensors can be very, very expensive. And what we ended up doing by using smartphones, by using very cheap sensors, we ended up building the whole system for 1/5 of the price. The cost of equipment that we have is like 1/5 or even 1/6 of the price. Now, but all the data now is also stored on the cloud servers. So once the data started coming into the cloud, that's where machine learning and deep learning came in. Remember, all this is literally, if you think about them, all of them, except your cameras, your accelerometers, ultrasound, your temperature, all of this is time series data. All of this is time series data. So the team started building some simple deep learning systems, nothing very concept, simple LSTMs, no complex systems. And the LSTMs, because this has never been tried on this data at this scale, right? And now we have actual data from the field. Simple LSTM models were detecting failures weeks in advance as compared to a rule-based system. So the moment we showed this data to the end customer, they were like, wow, this is superb. I mean, we can save millions of dollars over years by maintaining our systems better using just this data. Of course, a mechanical engineer doesn't know what an LSTM here is. So to solve this problem, we needed expertise in multiple areas. We needed mechanical engineers, obviously, because they are the ones who know how these systems work in the first place. We needed expertise in electronic systems, because we had to build, we had to get all these accelerometers, all of them. We had to make everything talk to a microcontroller. We needed computer science folks, right, for this application, because computer science folks wrote the code for microcontrollers, how to transfer the data, how to store the data on AWS, all of those things. And then finally, we had the machine learning guys creating actual business value end to end. So typically for IoT applications, you need expertise across multiple disciplines. Thankfully, I had some background in electronic systems, computer science, and machine learning. Again, I knew a little bit of electronics primarily because I used to play with Arduino boards during my spare time. I used to play with ESP32. I knew some of these systems. And when I first bought an Amazon Echo, I literally opened up the whole Amazon Echo, the Alexa device, right? I opened it up and I wanted to see what is there inside that. So I had that hacker mentality even as a student or even while I was working. So if I found some time, I would just open this up and see what all chips are there, how is everything working. But I didn't know much about mechanical engineering. That's where the core expertise came in. But the moment they told me about mechanical engineering and the mathematical concepts, look at this. The rule-based systems were using fast Fourier transform. They were using Fourier transforms and they were doing signal processing. That part I knew very well. Okay, because as a machine learning guy, my math is fairly strong, right? So I could understand these pieces, but of course, it took us some time to understand the mechanical aspects of it. Okay, but the whole team today has mechanical engineers, electronics engineers, computer science. The team right now is much more mature. They have people all across the board. But when they started off, they only had mechanical engineers, and we mentored them through the process over the last year and a half or so. Okay, so that's where we are. So I hope you got a good high-level overview of all the systems that are needed. Okay, that's why I wrote this list extensively. First, you need to solve a real-world problem, okay, which matters. Then you need sensors. Okay, then you need microcontrollers for edge computing to collect, of course, microcontrollers plus some electronic circuitry, sensors plus electronic circuitry. Okay, like your A to D converters, for example, right? So you need electronic circuitry. Then the data comes to your microcontroller. You transfer the data using Bluetooth, low energy, Wi-Fi, or 4G. Then you send all the data to your servers. Then you apply a bunch of rule-based systems based on the classical knowledge. Finally comes machine learning and deep learning systems. Actually, we showed with data to some companies which are early participants in this program that actually we can diagnose weeks before, thereby increasing the lifetime. Now here comes one more thing. There is one more sensor here that I was talking to you about, right? Cameras. Look at this. There are cameras here. So I said, okay, we know a lot of computer vision. We have studied a lot of computer vision and deep learning, and computer vision is one of my core areas of both expertise and my interest. Okay, then anyway, we were capturing the motor itself. Okay, suppose if you have a motor like this which is rotating, okay, we captured the camera view of the motors. Right now, there is some very interesting experiments that the team is doing. Again, to be very clear, this is not the team at Applied AI Course. This is a completely different startup that we are mentoring. Okay, the team at Applied AI Course and Applied Courses in general, we are fully focused on education itself, but we wanted to mentor a few startups in the initial days. So this team is a completely different team. This has got nothing to do with Applied AI Course, except for the fact that we're just mentoring them. Just wanted to make that clear. Okay. So as far as cameras is concerned, now I was reading some interesting literature on how to actually use the camera view of motors and diagnose problems from that. which requires a lot of advanced computer vision and lot of deep learning systems, or convolution neural networks, etc. So this is something that they've just started working on. Hopefully they'll have results in a year's time or so. Again, most of these things takes time. Most of these things take a lot of time. So you need a lot of patience. You need to be willing to learn new concepts if you want to build an IoT plus machine learning system. Okay, I hope you got some idea of how these systems work. So let me just go to the comment section and see if I can answer a few questions. If there is any, so after this, I hope with this big high level overview, we will jump into specific applications in healthcare, specific applications in farming. So now we know the architecture, right? We need sensors. So in healthcare, let's talk to what is the problem. Let's see what sensors are available, how some companies are already leveraging this, right? And what startups can be built on top of this today. Similarly, in smart farming, what are all the sensors? What is it that people are already doing? And how can we actually build new solutions on top of it? Then we'll summarize the whole architecture and the startup potential itself. Okay, here let me just go through this quickly, just to give you a context here. So if you think about it, if you take Uber, Ola, Lyft, all these startups, right? They're solving the problem of fast transportation. Their models are route optimization, pricing, all these models they build. What is their sensor? Their sensor is GPS. Okay. If you look at self-driving cars, which is a very important problem, companies like Waymo, which is a subsidiary of Google, Tesla, so they use state-of-the-art and deep learning algorithms. We have a case study as part of our course, which discusses how to build a fast-cut self-driving car. What are the sensors there? You have GPS, you have cameras, you have depth sensors, you have sensors in the cars also, right? What is the tire pressure? Okay, whether it is raining or not. So all these are sensors. Again, you can think of self-driving car also as an IoT application, if you think about it. Similarly, if you think of Amazon's Alexa, the speaker, or it's called Amazon Echo, or Google Home speakers, right? These are also IoT devices. These are smart home devices. What do they have? They have mic and speaker. Okay, the user gives the commands to the mic. I could say, hey Google, set up an alarm for 5 a.m. tomorrow morning. Okay, I actually have a Google Home and an Alexa, and I actually set up alarms mostly on these systems, apart from hearing to some music. Okay, so the mic is my input device here. Typical mic. When I talk to the mic, there is a lot of engineering, processing, all of that is happening, and there is a ton of deep learning to make the whole smart speaker possible. Right? Similarly, Fitbits, Apple Watches, all the smartwatch industry, right? Which is a big, beautiful industry today. It has accelerometers, heart rate monitors, all of them, and they use deep learning to do some very interesting things. Again, we have a case study on this as part of the course, right? Anyway, I'll discuss this in the healthcare applications. The next startup is something that you could build, okay? Because remember, one of the biggest challenges in this space is expertise across the spectrum of technologies. Okay, you need to understand the problem. For this, we needed mechanical engineers to understand the problem and to actually use it. We needed electronics engineers, we needed computer science engineers, and we need machine learning systems. So that's why these are harder to build, but once you build them, there is a lot of potential to solve lots of problems. Okay, so anyway, we'll continue the session with healthcare and farming applications in a little while. In the meantime, let me just change the view. Sorry, let me change the view. Okay, so 1 second. Okay, so let me just change the view and look at any comments that are here. Oh, good question. So let me answer a few questions and then we'll go to the second part. Okay, so a couple of questions here. Why are LSTMs used? Okay, so the reason we used LSTMs was primarily very simple. Because LSTMs are because the data that we're getting is time series data, right? Look at ultrasound data. It is actually sound waves, just that they're at a higher frequency than audible sounds, right? So we ended up using an LSTM because LSTM can process time series data. It's the simplest of models. Why use a traditional model? Why can't I just jump to an LSTM? Because LSTM can find some very interesting patterns that humans may not have found, right? Because we are sitting on a gold mine of data now. We can leverage the data using LSTMs. So even accelerometer data is actually a time series data. I think some of you have seen this, right? In our which case study? Yeah. So we have a case study in the course, which is called how do you build activity detection using accelerometers and Fitbit-like sensors. Okay, where we actually take the accelerometer data and we process it, right? And we felt LSTMs are state of the art. Why not use? Again, we didn't build a very complex LSTM. We built a very simple system, and it works phenomenally well, surprisingly. So very, again, just to play, again, the biggest problem with IoT is many companies don't want to share their data because their data is what they have. There are some competitions on Kaggle, you can just check them out, where you can get some data, but very often companies treat their data as their intellectual property, because data is super critical for this whole process, right? Anybody can build an LSTM model if they know basic deep learning, basic machine learning. Data is something that nobody has. Will Amazon give all of their retail data to you? No. Will Facebook give all of their social data to you? No. Does Google give all of the search data to you? No. Similarly, IoT companies don't want to just give away their data because it is a gold mine. It is a differentiator between your product and their product. Okay, so they treat it like intellectual property. So somebody is asking about the black hole images. Did they use IoT? No, they use scientific sensors. Okay, that's the next level. Okay, they have huge amount of scientific sensors. Again, I don't know much about particle physics and astronomy, but the level of equipment, the precision equipment they use is next level. It's not even industrial, it's at scientific precision level, right? So if you want to, you could call it IoT, because even a camera is an IoT device, right? Because camera is a sensor. At the end of the day, camera is a sensor which takes light as input, generates images or digital images as output. So if you want to call it, you could call it IoT, but that's like scientific level. This is not at, see the levels of sensors. There is consumer grade sensors, like what you have in your smartphone, right? You have an accelerometer, you have a gyroscope, you have a GPS. Those are called consumer grade, extremely cheap. You can buy them for, you can buy each sensor for like what, 15 cents, even for half a dollar. Okay, for 25, 30 rupees, you can buy each of these sensors. Extremely cheap. Then you have industrial sensors, okay, which are slightly more expensive. Okay, an industrial accelerometer could cost anywhere from 5,000 rupees to 20,000 rupees. Okay, so those are industrial accelerometers now. Next comes scientific and military applications. For example, you have GPS in my smartphone, but governments and defense systems have also GPS. They have satellite cameras. Those are extremely high precision stuff. So you have consumer grade, you have industrial, you have military applications. Finally, you have scientific computing, which is like the big deal stuff. So those sensors are hyper expensive. Okay. So if you want a camera at the scientific grade, that will cost you like, I mean, really high-end cameras. Like I'll tell you some experiments that I was playing around with called mass spectrometers. So spectrometers could cost north of like $20,000, $30,000. Okay, I want to play with something on spectrometers. I'll come to that in a little while. So I cannot cover the coding part of IoT ML. I think I mentioned this at the very beginning of the video. The primary problem being, I really want to, I wish we can do one other session on that eventually. Today, I'm giving a high level overview. Okay. But trust me, programming Arduino, programming ESP32s, programming Raspberry Pis, it's very, very easy. Okay. Arduino, I've seen like 12th class kids code Arduino. If you know any programming language, even if you know basic C programming language, let me show you a sample Arduino code. Okay. It's actually, just Google search for it, right? Arduino sample code. It's extremely simple. But of course, you need to understand the basics of microprocessors, microcontrollers, what are IO pins, what is serial transfer, what is duplex transfer, the basic concepts in computer organization or in microprocessors. You need to understand those basics. Without them, you'll not be able to code. But if you know C programming language, it's fairly straightforward, because actually you can code most of these in C, but they're also high level. They're also Python. You can also write code for Arduino in Python. You can write code for ESP32 in an advanced language called Lua. Okay, so there is a ton of modern programming languages that you can use to code in them. Unfortunately, I cannot go too deep into it because of the time constraint. Hopefully, we'll do something else in the future where we might be able to go into a deeper session. See, IoT is not similar to AI. I think that's a huge confusion. IoT is all about sensors, actuators. It is all about the microcontrollers, the electronic circuitry, which gives data for machine learning applications. Okay, I think that's how they're connected. IoT is not machine learning. Some of you may have that confusion. So it is this IoT is a way to obtain data which you can process and obtain value out of from machine learning and deep learning systems. So somebody is asking about edge analytics and mainstream analytics. So there is a huge problem in edge analytics. The biggest problem here is, even for example, see, edge computing is anything that is closest to the source of data. For example, you can think of my smartphone as an edge computing device, okay? Because the actual data that I use goes into my smartphone today, right? So my talking habits, my calling habits, my social media, my microphone signals, all of them. For example, today, if I just say, okay, Google, do something for me, okay? So a lot of computation actually happens. Okay, it's almost, I think it woke up, okay. So if I just give this signal to my smartphone, the microphone here is listening to it. Some processing is happening here. But when you do processing on a smartphone, a smartphone or any embedded device, any microcontroller, the biggest problem here is doesn't have too much compute, doesn't have, again, if you run some expensive stuff here, the battery will drain. So battery is the fundamental difference and computational part. Today there are smartphones, like for example, iPad with A12 chips has almost desktop level as a, okay, I think mine, okay. So I think the OK Google woke up my phone. So today, the Apple A12 processor in their modern iPads, they almost have laptop grade processors today. Okay, but the problem here is, so processor RAM is not a problem. I have an OnePlus which has 8 gigs of RAM. That's almost like a laptop that I used to have a couple of years back. So RAM is not a problem. Compute is also not so much of a problem because better processors are being designed using ARM and everything. Biggest problem is battery. You will literally kill your microprocessor or your laptop or your iPad if you run too much compute on that without giving power supply. So as compared to a server-based thing, I never have to worry about compute. I don't have to ever worry about power consumption, right? If I'm running something on my laptop or desktop or on a AWS cloud or a Google cloud, I just don't have to worry about power. That is one of the most important differentiator between doing any machine learning or analytics on a smartphone or any edge computing device versus a server in the cloud or a desktop. Okay, sounds good. Okay. Okay, so let me just take a couple of minutes break. I'll just take a quick water break. I'll be back by 11 or 11:01 p.m. Then we'll start the second part of the session. So I came back early because I see a bunch of very interesting questions here. So why don't the sensor companies let you export data? They're not sensor companies. They're actually companies which build predictive maintenance technology. So if they let me export the data, right, I own the data now, right? So when I export the data, they lose control over what I do with it. Okay, so they're very, very careful because that is like giving up their competitive advantage to a competitor, right? So there are a lot of these old school companies which are not moving to the next generation of technology, and they want to guard their data. Okay, and we talked to some really big companies and we asked them, do you have last 10 years worth of data? They're like, sorry, we don't have it. We just have last 3 months worth of data. We're like, what happened to all the data? They said this got erased from these devices, and these are big companies. These are like some of the best technology companies in India in manufacturing. Okay, they said we just asked them, do you have 10 years data? Then all this is not problem. We just gather all the data from you. Let's do all machine learning, deep learning on top of it. They actually didn't have data for the last 10 years. Okay, so that's what it is. Oh, so yeah, Google is actually doing, not just Google, many companies are doing this edge computing platform. Like for example, if I there's a very nice paper from Google research also, very nice paper. It's more of a Google engineering come research paper where they talk about their architecture for Google Now. Okay, when I say okay, Google set up an alarm at 5 p.m. or 5 a.m. whatever it is, right? So a lot of the compute is now done on this device. Instead of earlier in the previous versions, everything used to go to the server. That used to take a lot of time. Now they have actually LSTM and state-of-the-art deep learning models running as part of Android. Okay, so they're doing some amount, if not all. They can't do everything on a smartphone, but they'll try to do some aspects of it on a smartphone. Like for example, even for Amazon Alexa, right? So when you shout at it and say, "Hey Alexa," right? So that's called the wake word. That wake word detection, because it's always trying to listen to the ambient sounds, right? The moment I say, "Hey Alexa," it should wake up and start listening to my command. That wake word recognition, it's called the wake word recognition problem in smart devices. So that module has to be built into the device. It can't, every audio signal that comes to the Alexa box, it can't keep sending it to the server. That will be super expensive in terms of Wi-Fi consumption, right? In terms of bandwidth consumption, people will say, sorry, get out. So they do some of the pieces like, hey Alexa, or instead of transmitting the whole audio, they only transmit features computed from the audio to the server. They do some of these things as part of edge computing today. People are already doing it. People have been doing it for the last 3-4 years that I know of. So we don't have a plan to include IoT as part of the machine learning course, but if time permits, we might end up doing a course in the future for IoT. I really would like to do it again. I would need another collaborator who is also an expert in electronic system design, because my knowledge is still hacker type knowledge, not a very strong, experienced person's type of knowledge. So we don't have any plan right away. So that's, but we wanted our students to have the exposure to various pieces, right? We want our students to have exposure to how IoT and machine learning fits in. That's why we are doing this session, for everyone's benefit. How do everything fits in? That's one of the questions that we want you to have, at least a high level knowledge, so that you can take off from there. Suppose if you want to learn Arduino programming, just a Google search away. Actually, Arduino, the website for Arduino has a terrific tutorial on learning how to program. I remember, I think some 6-7 years back, maybe 6 years back, I wanted to learn Arduino programming. I ordered an Arduino from Amazon, all of those things. Then I picked up the whole Arduino programming and started building some simple systems over a weekend. Actually, real working systems over a weekend. That's how easy it is. If you know basics of programming, basics of computer science, it's extremely simple to do it, right? Okay, so now let's move to the second part of the session, where I'll also walk you through some very interesting examples. Okay, where are we? We are here. Okay. So the next thing is, given what we have understood for predictive maintenance applications, let's move on to, okay, so let me just hide this first. Okay. So let's move on to some more applications, right? So for example, here we have in healthcare, this is a very nice case study. Again, healthcare is something that I'm deeply passionate about, because here is a revolution which can help everyone from a newborn child to somebody who is 80 years old. Okay, I'll give you an example in how IoT and deep learning, or machine learning and AI, whatever I'll talk about specifically deep learning applications. Okay. So all of you might know about Fitbits, right? Fitbit is this smartwatch. I also wear one. Some of you may have seen me. And I mostly wear it for tracking my sleep and my exercising habits. Okay. So then there are Apple Watches, expensive devices, beautiful devices, very good. Okay. And what happens is these devices, there are also other smartwatches. There are smartwatches by Samsung. Okay. There are smartwatches by Huawei. There are smartwatches by Xiaomi. There are many smartwatch device makers now. What sensors do they have? They have accelerometers to measure if you're moving or not. See, imagine if I'm walking, there is a specific accelerometer pattern. Okay, I was telling you a while ago, right? We have a case study as part of the course where we actually got some data on how an actual accelerometer data from Fitbit-like sensors. This data was open sourced by a university. We got the data and we built machine learning and deep learning models on top of it to determine the activity that the user is doing. For example, we can easily detect whether the user is sitting, sleeping, climbing stairs, running, walking, jogging. You can detect all of those activities just using accelerometers. Okay. Many of them also have heart rate sensors now. Let me just show you this. Okay. Let me just show you this. Okay. I think just showing you this might help you. Okay. Stop this. Okay. So here is a Fitbit. Let me just show you an example, right? Here is a Fitbit watch. It's a smart watch. Now, if you notice, okay, I think you can see these blinking lights, right? You can see those blinking lights, right? Those blinking lights actually measure my heart rate. Okay, those two green blinking lights. Okay, those two green blinking lights, they actually measure the heart rate. Okay, so I just have to ensure that it is tightly. I just have to ensure that it is tightly there next to my wrist, and that's good enough, right? As soon as I do this, it starts measuring my heart rate. It actually measures that my heart rate right now is 90 beats per minute. Okay, it actually can measure my heart rate. Okay, just wanted to show an example there. So again, there is a huge spectrum and price points for these sensors. Apple Watch being one of the most expensive ones here. Okay, so there is also a barometer. What is a barometer? Measures altitude. Okay, for example, initially I was wondering, how does my Fitbit tell that I've climbed five floors, I've climbed 10 floors, or I've walked down 10 floors? How does it know that? So it actually has a barometer which measures altitude. So if I'm at this altitude, if I climb 5 floors, okay, 5 floors is roughly what, 50 feet, right? If I climb 50 feet, the barometer can read that. And during this, if I was actually walking and not going in an elevator or an escalator, right? If I'm actually walking, my hands will move, right? So if my barometer shows that, yes, he has moved 50 feet in altitude, and his accelerometer was also active, and his heart rate had also increased because I'm climbing upstairs, right? Of course, I would sweat, my heart rate would increase, all of them, right? So using all of this data, initially Fitbit, Apple Watch, all of them gave some simple stuff. It told us how well have you slept, how well have you exercised, right? Some simple stuff. I mostly use it for tracking sleep and exercise. Okay, they're also very good at counting the number of steps that you have walked. Okay, I mostly used to use it for this. Great. What else can be done? Because you're sitting on a gold mine of data. Again, to compute how much exercise has been done, how much sleep, how many steps, for all of them, you can write simple code. You don't require machine learning. You can have simple rule-based systems. You can have simple rule-based systems. For example, a rule-based system could be like this. If the accelerometer is not moving much and the heart rate has dropped and the barometer is not changing, which means I'm most likely sleeping, because when you sleep, your heart rate drops slightly, right? There is no movement in your accelerometer, which means you're in deep sleep. So today Fitbit can tell me how much deep sleep I had. In shallow sleep, what happens? My heart rate increases, I start dreaming, and probably I'm also moving. Okay, so it can measure how well I slept also today. And all of this doesn't require machine learning and deep learning. It just requires rule-based systems, simple code. Then comes this terrific company called Cardiogram. I was blown away by them. So they published a research paper in, I think, November or December of 2018. I love this research paper. Okay, Cardiogram is an interesting startup based out of Silicon Valley. They asked a very simple question. We have heart rate data, we have accelerometer data, we have some other sensors. Okay, there's also a gyroscope, if I'm not wrong. There is also a gyroscope in most smartwatches. So they realized that the Apple Watch is the best amongst all the watches in terms of accuracy, especially of heart rate. Okay, so people actually compared how accurately Fitbit measures heart rate, how accurately Apple Watch measures. So they looked at multiple devices and they figured out that Apple Watch has the most accurate measurement. Again, what do they compare against? They compare against medical devices. You have medical heart rate sensors, right, that you see in hospitals. So they saw that, okay, Apple Watch is doing very good. So they took the data from Apple Watch. And they started collaborating with University of California at San Francisco, which has a terrific medical school. So researchers at Cardiogram, it's a startup, okay, and UCSF, they published a research paper. I actually provided the link to this research paper also. Again, I'll share this whole doc with you at the end of it. This paper is called Deep Heart. Okay, look at this. This whole paper is called as Deep Heart. Okay, this is from a bunch of researchers at Cardiogram, and a bunch of researchers at University of California at San Francisco. Brilliant piece of work. Okay, again, AAAI is a very good conference. So I started taking these people more seriously because they actually published their research in a peer-reviewed journal or conference, which means they're not bluffing here. So what they've done here is beautiful. They've actually collected a lot of data. They've collected data from 53,675 patient weeks of data. So from every patient, if you collect 1 week of data, that's called one patient week. They have taken 57,675 patient weeks of data using these sensors. Okay. Now they use simple LSTMs. Their LSTM architecture is a joke. Okay, especially if you're a deep learning scientist, it's like very simple. But the data they have is the gold mine. The data is the gold mine. Okay, they took a lot of effort and time to collect this data. And now look at what all they can predict. They can predict diabetes with 85% accuracy. Diabetes is one of the biggest cause of death in the developed world, even in the developing world. A huge portion of my parents' generation suffers from diabetes. Imagine people wearing this watch. If I could die, they just wear a watch. Imagine if me wearing this watch, if it can tell me tomorrow that you are on the path to being a diabetic, I would immediately take necessary steps to ensure that I'm healthy. I would stop eating sugars. I would take care of myself. I would start exercising, all of that. It also can measure cholesterol, high cholesterol with 75% accuracy, high blood pressure. It can also measure sleep problems like sleep apnea. This is a very tricky problem. So people who have sleep apnea cannot go into deep sleep. I have family members who suffer from sleep apnea. Right? Look at these conditions. It is able to diagnose this, especially diabetes. Diabetes, high blood pressure, high cholesterol. Sleep apnea is not that common anyway, thankfully. Okay, for the other ones, it is doing a terrific job, and I don't have to buy any other sensors. I'm just wearing my smartwatch like an Apple Watch, and I'm able to diagnose all of them. That's the power of data. I mean, this is what is mind-boggling to me. Not just telling me how much I've slept. Again, this is all the data, pre-processing, all of that. Look at the deep learning model. That's all it is. Okay. So basically they have this multi-channel, multi-timescale sensor input data as a tensor. They have convolution, 1D convolution, LSTM layers, output nonlinearity, multitask softmax. That's it. Literally, that's all is their architecture. Like this is like super simple architecture. Literally one convolution layer, one LSTM layer, one output nonlinearity, most likely a sigmoid or a tanh nonlinearity, then a softmax layer. That's it. Like literally 5-layer network. I mean, this is not rocket science. This is like for somebody who has used deep learning all their for the last decade or so, this is like trivial. Okay, but the data is what they're sitting on. That's the gold mine. Okay, and they will never, to the best of, again, they talk about model architecture. They talked about multiple models that they trained. Okay, all the AUC curves, all of that. So look at the power here. So startups like Cardiogram, which are small startups, these are not your Apples and Googles of the world. These are small startups. They used existing devices, existing sensors, and state-of-the-art in deep learning to solve real medical problems. Imagine if we can increase the diabetes prediction to 90%. I would say that, and again, there are problems in the developing world. In the developed world, with diabetes being a major cause and heart attacks being a major cause of death or illness as people grow, this has huge societal impact. Okay, now what's happening here is more sensors are being added to Apple Watches and smartwatches. There is something called as a pulse oximeter. Okay, again, I started reading up about it just out of curiosity. A pulse oximeter measures how much oxygen is there in your blood at any point. Okay, very interesting thing. Okay, there is skin conductance. Okay, skin conductance basically says how much sweat. This can tell you how much sweat is there on your body. Okay, skin temperature can be used to measure how much of effort you're putting in your exercise. Like for example, if my skin temperature is much higher than the ambient temperature, outside temperature. So there is also a temperature sensor in many smartwatches today. Okay, if the outside temperature is 25 degrees centigrade and my skin temperature is, let's say, 38 degrees centigrade. Okay, that means, yes, And if my skin conductance is also high, this can measure how that I'm not just exercising, but how much exercise am I doing. Very important stuff. There is also ECG sensors that have come up in smartwatches now. Very interesting. Look at this. Of course, this is not like your proper medical grade ECG. I think medical grade ECG has 12 pins that they place all around your body. But I think these are typically your 2-pin sensors. And Silicon Valley, big investors like Khosla Ventures, etc., in Silicon Valley are investing in companies like these because they believe that this is the future of medical healthcare. Look at a country like the US, right? I think, if I'm not wrong, US spends close to $1.5 trillion on just healthcare costs. A country like US, $1.5 trillion is like massive amount of money. Okay, look at developing world like India and Africa and even China for that matter. Okay, where we can start to afford some of these sensors if you could diagnose healthcare problems early on, right? So the startup idea that if anybody is interested to pursue is, can you devise a $15 to $50 watch or band? Okay, between 1,000 rupees and 3,000 rupees in Indian currency. If you can make the sensors cheap, or if you can source the sensors in China cheap. Again, there are some Chinese manufacturers which are targeting this, like Xiaomi, like Huawei, right? All these Chinese companies have started working on building these sensors at a lower price point because they know that since they have manufacturing ability, if they can make these sensors cheap, like the way they've done it for smartphones over the last decade, everyone will wear a smartwatch and the medical impact from it is humongous. Okay, this is just one application, and I'll share this whole document. You can also read the research paper. It's very, very readable if you know basics of deep learning. The next very interesting area, very relevant in the context of India also, is smartphone. Okay, so what are the sensors here? Again, the most important part here for any IoT application, right? For most IoT applications, the sensors will change. The microcontrollers, Bluetooth energy, all of them will stay the same, right? The rule-based systems will be based on the problem. This will also stay the same. The machine learning, deep learning will change. So it is the sensors that change. It is the machine learning, deep learning systems that change. Rest everything is more or less the same. And of course, the problems themselves will change. Okay, that's the most important thing. The problems we are solving will change. For example, look at smart farming. Okay, again, this is already being done by some companies in the West. Okay, some large farming communities in the West and large farmers in the West have started this. The sensors are very interesting. Okay, you can have temperature and humidity sensor. Okay, you have soil moisture sensor. Again, with water scarcity becoming a bigger problem in India, soil moisture tells you how much you should water. Is it time to water your plants or not, or your farm? Illuminance sensor. This measures how much sunlight we are getting. This is very important in colder countries where there may not be enough amount of sunlight for farming, right? Electrical conductivity. Okay, again, you can measure how much nutrients, how much nitrogen is there. Okay, how much of the core nutrients required for plant growth are there using simple electrical conductivity. There are also something called as spectrometers. Very interesting concept. Spectrometers were actually scientific devices. Okay, so spectrometer, basically what it does in a nutshell, I'll tell you what it does in a nutshell. You throw some light at an object. Let's assume this is an apple. You throw some light, it absorbs some light, it reflects some light. Okay, based on what all it has reflected back and what all it has absorbed, a spectrometer, it's a scientific equipment actually. It can measure what all chemical compounds are there inside this. It can measure this actually. Okay, right now there are some very interesting startups which are building smartphone based spectrometers. They're not as accurate as scientific devices, but they're very interesting in the context of the speed and the cost efficiency. Somebody earlier in the comment section, I saw what are the applications of IoT in food. So imagine if you can measure using a simple smartphone spectrometer, right, whether the fruit is spoiled or not. Suppose if you work at a food factory, a food packaging factory, right? You could just have this smartphone sitting here. Each orange or each apple passes through this. It takes a photograph and it sees if something is spoiled or not. Okay, you can automate many of the food processing pipelines using smartphone spectrometers. Okay, you can also tell what are the chemical compounds that are there. If the surface of this apple is coated with insecticide, it should be washed before it gets packaged, right? So a lot of these sensors, again, from these sensoral data, a lot of interesting applications can be built. Again, in some countries like I think Norway, where they have huge amount of cattle, somewhere in Scandinavia. I forgot where Nestle is based out of. Nestle is a Dutch company, right? I forgot. Okay. So when they have tons of cattle, they literally started creating Fitbits for cows. They would actually have a cow neck band. So they're not called Fitbits, they're called neck bands. Okay. That would track everything for the cow, whether the cow is sick or not, whether the cow has fed the calf or not, how much it has walked, where all has it walked, how much pasture it has eaten. Right? Again, farming it doesn't just involve your growth of like paddy and rice and wheat. It also involves animal husbandry, like cows, right? So all these beautiful sensors are being now used to answer some very interesting questions. For example, okay, again, this is the first level of application. There is no deep learning right now yet. Okay, actually, I provided a hyperlink here. You can go here. There are some startups which are already working on this. Okay, for example, when should you water your plants? Again, there are some companies in Israel, okay, which have done some very interesting study using soil moisture sensors. Okay, this is with the help of Technion, which is Israel's IIT, okay, or Israel's MIT, whatever you want to call it as. Okay, so they've done some very interesting work to show, because Israel is a very dry, barren area. So they said, how do I use drip irrigation along with soil moisture sensors to decrease the amount of water required for the same output in my paddy growth or in my wheat growth? Okay, we can also measure how much insecticide we need. So for example, imagine if I have this whole plant. Again, this is being done at industrial scale right now. People have like thousand acres of land in the West. Okay, so they would just fly a drone. The drone has a bunch of special purpose cameras called infrared cameras, right? It also has some of these sensors, right? It sees that this part is getting infected by the with some insect, or this part doesn't have enough nutrients. So what it would do is it will send all this information to the farmer. The farmer only applies insecticide here. He only applies or he only puts in fertilizer only here. Rest everywhere where there is enough stuff. Why do you actually waste insecticide or fertilizer? This is very expensive for many farmers in the world. So by decreasing the insecticide and fertilizer being applied using smart farming and sensors and cameras, a farmer's profit margins will increase. Right? Now, if there are, again, in some countries where they have greenhouses for large scale growth, they want to understand how to maintain the temperature for growth. There are urban farms nowadays, not yet in India, but elsewhere in the world. Right? So these are all real world implications on improving. Imagine if you can mine this whole data using deep learning and machine learning algorithms, and if you can reduce, at the end of the day, the farmer, if you can reduce the cost of producing, let's say, 1 ton of wheat. Okay, if today's expense is X, if you can reduce it to 0.8x, the cost of production, same production, or if today we are producing X with the same resources, if you can produce 1.5x, look at the profit margins that the farmer gets. And this technology is not that expensive. Farmers also today in the developing world, like in Africa, in India, in China, many of them have smartphones, right? So all these sensors can be directly connected to smartphones themselves, right? So there is a lot of opportunity here. But the big question here is, most of these solutions today work for large farms. How do you solve this problem? The big question in the context of in India and Africa, the big question here is, how do you solve this for small scale farmers who might have just 1 acre of land? Or I think the government definition is anybody who has less than 5 acres or 3 acres of land in India is called a small scale farmer. How do you build solutions? Again, a small scale farmer cannot invest thousands of rupees on technology, but he or she might already have a smartphone. Can you build something on top of smartphone to provide these data to them, to provide value to them? Okay, either by reducing their costs. Again, this is I'm very sure in the next 5 to 10 years, this area will be disrupted, not just in India and Africa. It's already being disrupted in the West. Okay, I'm sure some smart kid sitting somewhere in their study room will figure this out. I'm very sure about it. Okay, so broadly speaking, this is the architecture or the tools that you have to have. Sensors, what sensors do you want? Edge computing, either Arduino, Raspberry Pi, ESP8266, or smartphones. Okay, how do you power everything? By solar or by battery? Again, there are a lot of applications in agriculture. Okay, there are a lot of applications in agriculture where people use a small solar panel to power their Arduinos, Raspberry Pis, ESP8266, or smartphones. Okay, the whole, again, lot of these large servers, large cloud players like Microsoft Azure, Google Cloud, AWS, there is something called AWS IoT, which helps you stream data from these devices to the server. It would store all of it. It will give you basic analytics and all of that. Of course, for machine learning AI, you have TensorFlow, Keras, Scikit-learn, XGBoost. So this is your toolkit. This is the toolkit that you'll often play with in the intersection of IoT and machine learning. Okay, so I hope this whole session gave you a good high-level overview. Again, we couldn't go too deep into it just because of time constraints. But again, I'll share this document itself. There are some nice links. For example, if you want to read about Cardiogram's work, the research paper here, the smart farming applications, I think this is also a nice link that I've provided here. Smartphone spectrometers right now that are coming into market, right? So I've provided some links here and hope they'll help you here. Okay, so let me just go to the comment section and see where we are. So I thought I'll spend some half an hour, or I'll spend some time answering questions. So if anybody has questions, I could take some of them now. Okay, if there's any question, I could take these questions. So feel free to put them in the comment section. I'll try to answer as many as possible over the next 15-20 minutes or so, right? So the basic thesis of this is, how does everything that you're learning in machine learning or you're planning to learn in machine learning fits into the IoT sphere? Okay, IoT is one way to get or to obtain sensor data. Again, I believe, sensor data is unlike human data. For example, if I add 10 friends, right, that's 10 pieces of information that I'm giving to Facebook. Okay, sensor data is continuous. Okay, I just have to put in a sensor here. For example, imagine if I put in a temperature sensor here in this room. I keep getting the data as long as there is battery in the device, right? So once you put in your sensors and your devices, obtaining data is much more easy. And once you obtain the data, you have the gold mine of techniques. And you have, first of all, you have the gold mine of data, on top of which you can build a ton of machine learning, deep learning applications. But remember, whatever you're building, create value at the end of the day. If you're a startup guy, if you do not create value for your end customer, you're just wasting time. Sorry, what are the questions here? What is the scope of ML IoT in pharmacy, medical insurance? Actually, I forgot to mention this. Very good question. So there are two other very nice applications of IoT. So let me walk you through a couple of them. So this is in both medical insurance and automotive insurance. For example, in medical insurance, there are some companies like Cigna in the US. I think Cigna is also there in India now. Cigna works with TTK, which is a long-time player for healthcare insurance in India. So Cigna is working with companies or with Apple Watch, Fitbit, saying that if you wear a Fitbit and if you stream the data, based on the data, we can reduce the price of the cost of insurance itself. Because imagine if I'm exercising daily, my health is more likely, there's a higher probability that I'll be healthy, right? If I'm getting good 6 to 8 hours sleep every night, right? If I'm exercising well, if I'm not going through too much stress, then my insurance rate should drop, right? So that's one experiment that companies are doing. Both insurance companies as well as tech companies are trying to work on that. The second type of insurance is automotive or automobile insurance. So companies have started working with sensor companies, IoT companies, wherein they'll ask you to plug a device. So most cars have this port called as, what is that port name? I keep forgetting that. There is a port under your car driving wheel. I forgot. I'll have to search for it. I don't remember at the top of my head. So there is actually a port. The name is, I'm almost getting it. Anyway, so there is a port where you can connect a device and it would gather all the data about your car. For example, it could collect data like how sharply do you brake, how fast you accelerate, okay? All those measurements, and they can help automobile insurers understand whether you're a careful driver or a careless driver. Okay, again, I've seen companies that are building these solutions for parents of teenagers. Teenagers are the biggest headache for automobile insurers because teenagers don't drive safe, they're little rash, they're careless, all of that. That's why insurance rates for teenagers is the highest in the world, in the US, in India, everywhere. So as you grow older, as you start having kids and all of that, your insurance rates drop because people consider you to be more responsible. So now there are sensors that I've seen a few parents in Silicon Valley plug it to the kids' cars, right? So they would just plug in this sensor and it would track. And if there is any red flag that the kid is speeding up or anything, there's a message directly sent to the parent. So this hopefully increases the safety of younger drivers, thereby reducing the cost of insurance itself. And even insurance companies, I think, what is this? Geico, a very popular insurance. I think the second largest insurance company in the US for automobile. They're also working on some technology wherein they'll give you a sensor, you plug it in. If you plug it in and if you don't remove it, some rules, they can reduce your insurance prices. Okay, so it's called OBD port. Thank you. Somebody said that. Yes, it's called as OBD port, onboard diagnostic port. Yes, thank you very much. So somebody is asking about the material for today's lecture. It will be available on YouTube itself, so don't worry about it. The Google Doc itself, I will put it as the first comment and I'll pin it. Okay, so this video is public, so you'll have it if you want to access it at a later point. Don't worry about it. We'll continue to keep this video public even after the live session. So it will be here, and I'll also share the Google Doc link, as soon as this session gets over. Okay. Okay. So smart cities, actually, I'm not an expert in city management or anything, but I can certainly see a few things as somebody who lives in a metropolitan area, who drives every day to work. I wish, especially in a city like Hyderabad, right? Again, this is my personal opinion. What if the signals, the traffic signals are automated based on, see, right now, what happens is a police constable or a SI or an ASI has to sit at that junction and constantly up or down the signals based on the traffic flow, depending on the time of the day and depending on the weather conditions. It's very painful for them. Why can't we just automate it? It's so easy to actually put in a smartphone there with a reasonable camera. It analyzes how much traffic is there on each side. And even instead of having, like, for example, we have some roads which are 2 lanes on one side, 2 lanes on one side. Okay. Now, let's say early morning hours, the whole traffic is flowing this side. Why can't we just make everything in one way there? So I hope that there are certainly some traffic management systems that are possible using cameras, sensors, and things like that. Again, this is done in some places of the world. For example, I think IBM built some system like this both in Singapore and in some Scandinavian country, where they would charge a premium if your car uses some roads during peak hours. So by force, that is to force people to actually use public transport in countries or cities where they have phenomenal public transport, right? So there are some very good IoT machine learning applications. Again, when you're capturing data from camera, you have to build convolutional neural network models. All the deep learning stuff, you'll have to start building it, right? So those are some of the interesting things that you can build for smart city applications also. Machine learning and blockchain. There are some applications, but let's not discuss it today. Probably we can do a live session on that topic at a later point, because I don't want to give you a half-hearted answer there. So Cardiogram, I think their product is still in beta, because to launch a product like that, not just in US, but in any country, you need to get FDA approval in the US. It's a Food and Drug Administration. So if you're launching any medical grade device, and if you claim medical grade stuff, you better get FDA approval, otherwise it's a nightmare. Okay, I think Cardiogram is working on improving that system and also getting medical grade FDA approvals. Okay, sounds good. Okay, folks, I think this was a good session. So nice. Thanks everyone for joining in, and I hope I could answer a few questions. And okay, somebody, what is the scope for ML in designing embedded systems? That again, if you want to design embedded machine learning applications, I'm sorry, which is how do you build a machine learning model on a microcontroller? That's a different beast altogether, because you don't have enough compute, you don't have enough RAM, which means your models have to be very simplistic. You don't have enough battery, which means you can't do too complex a code. Okay, in such situations you end up using very simple code, or you start writing special purpose PLAs. There's something called as programmable logic arrays. I think PLA is programmable logic array, right? Again, I'm no electronics guy, so please bear any excuses that I might make. So these are actually where you can write code which runs on the hardware. Okay, it's literally like a programmable array of computational units. Okay, so there is also some work on that front where you have PLAs on which you can write this code, but that's a beast altogether. Like, to be honest, I'm no expert in that because I've not done it. I've seen people do it. I've learned a little bit from them. The key idea is this: in embedded systems, you don't have compute, you don't have a lot of RAM, you don't have battery, which means you can't run any complex models. You have to run as simple model as possible. If you're using general purpose microcontrollers, if you're designing your own special purpose microcontroller, for example, Apple did this, right? Apple has this A12 or A13 chip with a bionic chip. So Apple literally designed a special sub chip in their chipset to do all of the state of the art AI. For example, Apple today on iPad, right? It automatically unlocks by just looking at me, right? So all of those advanced systems that Apple has, Apple actually has built a special, it's called the Apple Bionic chip, if I'm not wrong. So large companies like Apple are building their own chips, special purpose AI chips. I think Qualcomm also has a special purpose AI subcomponent in their modern 855 chips. Qualcomm 855, Snapdragon 855 chips, right? So the chip manufacturers are designing special AI components, just like the way Apple did with their ARM processors and Qualcomm did with their Snapdragon processors. I thought Intel was also doing something on those fronts, right? So if you have those special purpose components, you can speed up things, because those hardware that's not a general purpose CPU. It's not a general purpose CPU. It's a very specialized hardware. It's not even a GPU. It's a very specialized AI chip. They're calling them AI chips now. So that can help you learn. I think most of them are being developed for deep neural networks. So they're very fine-tuned for convolutional neural networks or LSTMs, and that certainly can do. So there is expertise at multiple level to do that. You need low-level hardware, you need firmware, you need memory management. So a lot of the systems knowledge is also needed in addition to just machine learning knowledge. Okay. Yeah, so you can always send your data to the server where more complex models can be run, but there will be instances where you want to run some models locally, like the example that I told you, right? The Alexa wake word, hi Alexa, or okay Google. You want to run those models which detect these keywords on the device itself. Okay, folks, do you have scope in ERP? So enterprise resource planning, actually there are some applications that I've heard of. Again, I don't have expertise in ERP, so I'll not be a good judge of it. But something that I've seen companies do, like large companies like Walmart, etc., for their supply chain optimization. Okay, so they have lots of sensors. Okay, be QR code, barcode, weight sensors, all sorts of sensors through which they have optimized the whole supply chain much better. I'm sure the supply chain management team at Amazon and other e-commerce companies also do that. Okay, so but to be honest, I don't have first-hand experience of ERP, and hence I will not be able to give you too deep of applications around ERP. Sorry for that. Sounds good, folks. I think we had a good session. Thanks for joining in on a Sunday. And as some of you have requested, we'll try and do more of these public live sessions. Again, I do not want to promise you a frequency like once a month or anything. I don't want to make that promise right away, but we'll certainly try to have regular public live sessions on general topics like this. Again, in a public live session, I may not be able to go too deep into one topic because everybody may not enjoy that, number one, and everybody may not have the prerequisites to go too deep on the topic. That's why for public live sessions like this, we're trying to do more broad topics to give you a 10,000 feet view. Like, how does IoT and machine learning fit in based on our own experiences, what we've seen, what we've learned, etc. Right? So nice talking to you, and we'll try and do more of these public live sessions more regularly than what we've been doing over the last couple of months. See you folks. Thank you very much.